Welcome back to lecture 18, Rolle's theorem and mean values theorem. This lecture is a application of continuous and differentiable function, and it is very useful in finding the solution of a function in some intervals. So let's start. What is Rolle's theorem? Let fx be a function such that fx is continuous. First condition is fx is continuous on closed interval a comma b. It means function is defined on closed interval a comma b. Domain is closed interval a comma b. Now, continuous on closed interval a comma b, I have already discussed in continuous and differentiability lecture. It means function is defined for all points between a and b, and right hand continuity at a and left hand continuity at b. More on this you can see in my previous lectures. Second condition is fx is differentiable on open interval a comma b, means it is differentiable at every point between a comma b. Third, if fa equal to fb, means the value of function at a and b is same, then there exists at least one point C belongs to open interval a comma b, at which f dash c is equal to 0. F dash c equal to 0, such that tangent at point C becomes horizontal or parallel to x-axis. What is the meaning of this? Let's see geometrically. Suppose we have a function fx between closed interval a comma b, it is continuous, and in open interval a comma b it is differentiable. At a, the value of function will be fa if this is your y equal to fx function, and at b the value at b is also fb, and fb is equal to fa. This is the condition which is satisfying here. Then you have if any point c in this interval only, at which derivative of fx at c is 0. Or you can say that the slope of this tangent at c is parallel to x-axis, or theta equal to 0 degree, parallel to x-axis, or it become horizontal. Means derivative of fx at x equal to c equal to 0. And what about c? C belongs to open interval a comma b. This is the meaning geometrically. It is not necessary that always there exists only one c. It is at least one. Means the values of c can be more than one also. What is the meaning of this? We can suppose any function like this only. Suppose at a the value is fa, and b the value at b is fb. This is same, but function look like this. Then you have more than one c. It can be this is c, this is your c, this is your c, this is your c. So you are getting more than one c which is lying between open interval a comma b. but the condition is function must be continuous and differentiable in the given intervals. This is the Rolle's theorem. Let's check the applicability of Rolle's theorem in some functions. First, fx equal to mod x on interval minus 1 to 1. Check the applicability of Rolle's theorem of fx equal to mod x in interval minus 1 to 1. What about mod x? You know the graph. You can see my lecture 14, prerequisite for calculus module. The mod x function can be drawn like this. Between minus 1 to 1, if you draw the closed interval, which is given domain here, the function is continuous. Fx equal to mod x is continuous on the given domain minus 1 to 1. I'm satisfying your third property. I'm skipping second property. Why? I will tell you after some time. F at minus 1 is mod of minus 1 is 1. And F at 1 is mod of 1 equal to 1. Means if you compare with this closed interval a comma b, a is equal to 1 and b equal to 1. A equal to minus 1 and b equal to 1. So F1 and F minus 1 both are equal. It means condition is satisfying. But Fx is equal to mod x is not differentiable at x equal to 0. You can see my lecture 16. I have discussed on differentiability of modulus function in detail. And 0 belongs to minus 1 to 1 open interval. It means this function is not satisfying the conditions for applicability of Rolle's theorem, so we cannot apply Rolle's theorem. We cannot apply Rolle's theorem. Second example, Fx equal to tan x. Fx equal to tan x and Ax is between 0 to pi. Close interval 0 to pi. If you compare, then A equal to 0 and B equal to pi. Between 0 to pi, if you draw the graph, 0 to pi, and this is your pi by 2. We know that at pi by 2, we have an asymptote. So the graph is look like this. Graph is look like this. And this is your 3 pi by 2. It means if you see this graph, function is breaking at pi by 2. Means what is the meaning? If you go limit x tending to pi by 2 minus, means the left hand limit at pi by 2, it is limit h tending to 0, f of pi by 2 minus h is equal to limit h tending to 0, tan pi by 2 minus h is equal to limit h tending to 0, tan 90 minus theta is cot theta, and it tending to infinity. It's tending to plus infinity. And you can see that when x is less than pi by 2, it is tending to plus infinity only, because asymptote is going to be at plus infinity. But what about right hand limit at pi by 2? And why we are discussing at pi by 2? Because pi by 2 is lying between in this interval. If you go for right hand limit, it is f of pi by 2 plus h. It is limit h tending to 0, tan pi by 2 plus h, limit h tending to 0 minus cot h. Tan 90 plus theta, it will be in second quadrant, and second quadrant tan is negative, and it's tending to minus infinity. You can see at x pi by 2 plus, the value is going to be minus infinity. It means LHL and RHL does not have same tendency One is tending to plus infinity and another is tending to minus infinity. So limit does not exist. It means function fx is not continuous at x equal to pi by 2. Another way to check, on the drawing of this graph, you have to lift the pen at pi by 2. At drawing at pi by 2, you draw this line. It is an asymptote at minus pi by 2. When you draw this curve, you have to lift the pen. It means at pi by 2 function is not continuous. Not continuous at pi by 2, which lie between 0 to pi. It means we cannot apply Rolle's theorem on this function in this given interval. Another example is fx equal to 3 plus x minus 2 to the power 2 by 3, and interval is from 1 to 3. Check the applicability. I am giving you as a homework this question, and I am telling you we cannot apply Rolle's theorem here because the differentiability will not satisfy at x equal to 2, which lie between open interval 1, 3. It is a homework for you. One important remark. This is the most important remark. Converse of Rolle's theorem. Converse of Rolle's theorem is not necessarily true. Means if a function has a root in some interval, or if a function has derivative is 0 in some interval, it may not satisfy the conditions of Rolle's theorem. For example, if we take a function fx, x cube minus x square minus x plus 1 on the interval minus 1, 2. This is a polynomial function. So polynomial functions are everywhere continuous and differentiable in the entire real line. So these two conditions are already fulfilled by these polynomial functions. Only we have to check fa equal to fb. Now we are searching for phi first stage. Then we will see the third condition of Rolle's theorem. So if you take derivative of this f dash x differentiation, we can do 3x square minus 2x minus 1. Now f dash c for some c, for c f dash c equal to 0, then 3c square minus 2c minus 1 equal to 0. If you factorize it, 3c square minus 3c plus c minus 1 equal to 0. If you take 3c common, c minus 1 plus 1, c minus 1 equal to 0, c equal to minus 1 and c equal to 1 by 3. You can see that both the c are lying between minus 1 and 2. But if you satisfying the third condition on comparing with closed interval a comma b, then f at minus 1 is not equal to f at 2. You can verify that. It means, what is the general statement for this theorem? If a function is continuous on closed interval a comma b, if a function is differentiable on open interval a comma b, f equal to fb, then you have at least one c in open interval a comma b such that f dash equal to 0. But if a function is not satisfying Rolle's theorem condition, it may also have derivative at some point 0, or tangent is horizontal at some points in the given interval. But if the conditions of Rolle's theorem is satisfying by any function, then you have always at least one c in open interval a comma b where f dash equal to 0. But if the conditions are not satisfied, you cannot claim that we cannot have horizontal tangent. We can also have horizontal tangent if the conditions are not satisfied. Let's verify Rolle's theorem in some examples. Means we have to find some c. First is fx equal to x square on closed interval -1 to 1. It is a polynomial function, so continuous and differentiable on the entire real line. We have to take no tension for this function. We have to check f equal to fb, f at -1 is equal to -1 square is 1 and f1 equal to 1 square is 1. So all the conditions of Rolle's theorem are satisfying. Now to derivative. So f dash x will be 2x, f dash c will be 2c, and if you put f dash c equal to 0, it will give you 2c equal to 0, c equal to 0, which is lying between -1 to 1. It means we have that point x equal to 0 between -1 to 1. If you draw the graph, it will look like this only. At c equal to 0, it means origin, we have a tangent, and that tangent is horizontal or coincident or parallel to x-axis. That's why we call it generally horizontal tangent, because in that if c equal to 0, then tangent can be coincidental to x-axis or coincide with x-axis. So we have this tangent. It means x-axis is itself a tangent for this point. Second example we have fx equal to verify the Rolle's theorem 2x cube plus x square minus 4x minus 2 when x belongs to -√2 plus √2. It is a very basic problem based on you can also solve this problem as previous example, and you will get c equal to you will get in this problem is equal to the f dash c equal to 0. If you put c is -1 and 2/3. Now we have another mean value theorem. Rolle's theorem is not mean value theorem. Intermediate mean value theorem. This is your mean value theorem, and it's given by Bolzano, a famous mathematician. So what is the statement of this theorem? If fx is continuous function in closed interval a comma b, and fa fb less than 0, means what are the possible conditions? Suppose this is your closed interval a comma b, product is less than 0, it means both have opposite sign, means there is a possibility that at x equal to a, fa is positive, and x equal to b, fb is your negative. Or this can be also look like this: at a equal to x equal to a, fa is negative, and x equal to b, fb is positive. Means both have opposite natures. Then it has at least one real root in open interval a comma b, where fc equal to 0 and c belongs to open interval a comma b. Means you have a root. You can see that this is your x-axis, and at x-axis this function is cutting. It means here y equal to 0 or fc equal to 0. This function is 0. C is the root of this function. Here this will be your c. And in the important point is that at least one is always odd number. It's always odd number. There will be root like 1, 3, 5, 7. Roots will be in the odd number. So this is your intermediate mean value theorem. If fa and fb have opposite nature, then there will be one root between a and b where function will be 0. I will solve one problem based on previous year after some time. Next is Lagrange's mean value theorem. This is a also generalized form of Rolle's theorem, or you can say that for a particular case, Lagrange's theorem will become Rolle's theorem. Let fx be a function such that fx is continuous on closed interval a comma b, fx is differentiable on open interval a comma b, then there exists at least one c belongs to open interval a comma b such that f dash c equal to fb minus fa over b minus a. What is the geometrical meaning of this statement? Or tangent at c, this will give you the slope at point c, becomes parallel to the chord joining a comma fa and b comma fb. What is the geometrical meaning? You can see by the graph. Suppose this is your closed interval a comma b. Here fa is not necessarily equal to fb. Suppose at a the function is fa is here, and at b this is your function. fb is this value. So the coordinate of, suppose this is your a point, this is your b point. Coordinate of a will be a comma fa small, and coordinate of b will be b comma fb if this is your function y equal to fx. Now there will be a c between, this will be your c, this will be your c, where f dash c is equal to fb minus fa upon b minus a, or this tangent is parallel to this chord. When parallel, both the lines are parallel, it means slope will be equal. So slope of this tangent at any point c, f dash c, will be equal to the slope of AB chord. And you have the coordinates of AB chord is x1, y1, x2, y2. Then the slope is given as y2 minus y1 upon x2 minus x1. Slope of tangent. The formula is y2 minus y1 upon x2 minus x1. So y2 will be fb minus y1 will be fa upon b minus a. This will be used. And you will get always at least one c between this open interval a comma b, where the tangent is parallel to this joining chord. There will be at least one c, means you can get more than one c also. More than one c also means in that case the graph will look like some another form, or you can say that the graph can be c. If you see here, this can be c like this. Between a comma b, you can get more than one c. This is your c, this is your c, this is your c, this is your c, and all these slopes will be parallel to slope of this chord. Let's see some example. Verify Lagrange's mean value theorem in closed interval 0, 4 for fx equal to x minus 1, x minus 2, x minus 3. If you multiply x minus 1, x minus 2, x minus 3, it will give you a polynomial x cube minus 6x square plus 11x minus c. This polynomial is always continuous and differentiable in the entire real line. So continuity and differentiability, both the conditions are satisfying in the entire real line, and 0, 4 is a subset of R cross R. Means this is also real number, this is also real number. Or you can say this is a subset of minus infinity to infinity. Okay. Now we have to check fa equal to f. F at 0 will be, this will be your a comma, if you compare, then 0 will be a and b will be 4. F0 will be minus 6 and f4 will be 4 cube minus 6 into 4 square plus 11 into 4 minus 6. You can check, it will give you 6. Now for c, we have to derivative f dash x, and the differentiation of this function will be 3x square minus 12x plus 11. So for any particular c, f dash c will be 3c square minus 12c plus 11. Now put the Lagrange's theorem statement. F dash c equal to fb minus fa upon b minus a. If we find such c which belongs to open interval 0, 4, then Lagrange's mean value theorem will be satisfied. So f dash c will be 3c square minus 12c plus 11 is equal to fb means 6, fa will be minus plus 6 upon 4 minus 0. So 3c square minus 12c plus 11 equal to 3. If you solve this, you will get c equal to 2 plus minus 2 root 3 by 3. And both these values are belonging between open interval 0, 4. At least one value, means more than one can be also belong. But in the intermediate mean value theorem, at least one is always odd number. But in the other mean value theorem like Lagrange's and Rolle's, which is not actually mean, the values can be in even number also, 1, 2, 3, 4. Next theorem is Cauchy mean value theorem. This theorem is generalized. One remark is left in the Lagrange's mean value theorem I want to discuss here. If you take in particular, what is the remark here? If fa equal to fb in particular, then and a is obviously not equal to b because it's a closed interval, then f dash c will be 0 and it will reduce to Rolle's theorem. If f equal to fb, which is a particular case of Lagrange's theorem, then this theorem will reduce in the Rolle's theorem. Now, Cauchy mean value theorem. It is a generalization of Lagrange's mean value theorem, or it can be say that it's a comparison of two functions. Let fx and gx be two functions such that both fx and gx are continuous on closed interval a comma b. Second, both fx and gx are differentiable on open interval a comma b. Third, then there exists at least one c belonging to open interval a comma b such that what will be the condition for f fb minus fa upon b minus a equal to f dash c and gb minus ga upon b minus a equal to g dash c. This is your Lagrange's mean value theorem. If you divide both function f dash c upon g dash c, then f dash c upon g dash c will be fb minus fa upon gb minus ga. It is nothing else Lagrange's mean value theorem for two functions. So this is your Cauchy mean value theorem. Now we will solve some previous year question asked based on mean value theorem and proof theorem. The first question is, the Lagrange's mean value theorem is satisfied for fx equal to x cube plus 5x in the interval 1, 4. It is given that it is satisfied already. Means we do not need to check the continuity, differentiability and everything. But if you see this is asking in open interval a comma b, then uh, we are supposing that the Lagrange's mean value is satisfying. It means it will be satisfied in 1 comma for closed interval. It's satisfying. So we have to take closed interval. And what is the statement that f dash c equal to fb minus fa upon b minus a? Because we need the value at the boundary point. It means we have to discuss in the closed interval a comma b. If you compare with a comma b, yeah, a will be 1 and b will be 4. So f4 minus f1 upon 4 minus 1. F dash c, how you find f dash c? F dash x will be look like 3x square plus 5. Then f dash c will be 3c square plus 5. 3c square plus 5. Now put all these values here. So it will be 3c square plus 5 is equal to f4, it means 4 cube plus 5 into 4 minus f1 1 cube plus 5 into 1 upon 4 minus 1. So 3c square plus 5 is equal to 6484 minus 6 upon 3. It is your 78 by 3. It will give you 26. So 3c square is equal to 21. C square is equal to 7. So c will be plus minus root 7, or c will be plus 2.645 and c will be minus 2.645. Both you will get the plus and minus, and this value is belonging between 1 comma 4. This will not satisfy Lagrange's mean value theorem, and because we need at least 1c, and you are getting 1c here, which is 2.645 between 1 comma 4. So answer is 2.645. So you are interested in the value of c, and the applicability of Lagrange's mean value theorem is given, is satisfying here. Second problem is a function fx is defined in the closed interval 1 minus x square plus x cube in the interval minus 1 comma 1, for which the mean value theorem is satisfied. Firstly, if we see, this is a cubic polynomial and it will be continuous and differentiable everywhere. So no need to worry about the differentiability and control and continuity. We have to check fa and fb. If we compare with a comma b, then f at minus 1 will be 1 minus 1 minus 1. It will be minus 1. And f1 will be 1 minus 1 plus 1. This is equal to 1. You can see that f minus 1 is not equal to f1. So we can't apply Rolle's theorem, because for Rolle's theorem fa must be equal to fb. In this case, the name of theorem is not given. We have to apply, and it is given the mean value theorem is satisfied. It means we have to go for Lagrange's mean value theorem, because there is only one function. So there are two possibilities. We can apply Rolle's theorem or we can apply Lagrange's mean value theorem. But Rolle's theorem conditions are not satisfying here. So we have only one choice, that's Lagrange's mean value theorem. So we have to find that c between minus 1 to 1. So f dash x look like now, it will be minus 2x plus 3x square. So f dash c will be minus 2c plus 3c square. For f dash c, we apply Lagrange's mean value theorem. It is given as f dash c equal to fb minus fa upon b minus a. So 3c square minus 2c is equal to fb means 1 minus minus plus 1 upon b minus 1, 1 plus 1. It means 3c square minus 2c equal to 1. If you solve c, you will get c equal to minus 1 comma 3 and 1. Minus 1 comma 3 is lying between minus 1 comma 1, but 1 is not lying between open interval minus 1 comma 1. So I think there will be a correction here in the question. Here both values are not belonging. This value is not belonging to minus 1 comma 2. This value is only belonging to minus 1 comma 2. We have to check in the open interval. So make a correction. Minus 1 to 2 open must be. There will be open interval on the boundaries. And the last question is, a function fx is continuous in the interval 0, 2. And it is known that f0, f2 is minus 1, f0 is equal to minus 1, and f2 equal to minus 1. And f1 is also given to you 1. Which one of the following statement must be true? Now, if you see and read the question carefully, the function is given only continuous. The differentiability condition of this function is not given in the question. It means we can't apply Rolle's theorem, Lagrange's theorem, or Cauchy theorem, because for these theorems, the differentiability condition of fx is required. It means we have only one condition, one theorem, that's intermediate mean value theorem, where only the continuity of the function is required. So how you will tackle that problem? In that problem, if you remember the statement of IMVT, it's a function is continuous in the closed interval a comma b, and the function, the value of function at boundary point has opposite sign, then you have at least one solution in open interval a comma b such that fc equal to 0, where c belongs to open interval a comma b. Now if you see, there are two type of function, fy plus 1, fy f2 minus 5, and fy and minus f of 2 minus 5. Firstly, check these three cases, then we will see for b option, why b option is not. If you see b part, I'm taking b part, fy minus f of 2 minus 1, there is a one function I'm taking at gp function, and I'm taking as a difference fp minus f of 2 minus p for any p, where p belongs to 0, 1, close interval 0, 1 I'm taking. Now if you take in p in 0, 1 I'm taking here, close interval 0, 1 I'm taking, not in open, see, then g0 will be f0 minus f2, and f0 and f2 both are same, then g0 is 0. What about g1? G1 is f1 minus f2. It is 1 minus 1 plus 1. It means g0 into z1 is equal to 0. We cannot apply intermediate mean value theorem here because we want less than 0, opposite sign. So B option we cannot make any comment. What about D option? In that case, we take GP as Fy plus f of 2 minus 1. We are taking the function from right to left, and P belongs to closed interval 0, 1. Then G0 will be F0 plus F2, and it will be minus 2. G1 will be F1 plus F at 1. F at 1. It will be F1 minus F1. It will be 0 actually. It will be 0. Make a correction here. F1 minus F1. Then it will be 0. So we cannot make any comment here. F1 plus F1, it will be F0 plus F of minus, if you put y, P, take P, no? Then GP, P2 minus P. So G0 will be F0 plus F of 2, that will be minus 2. G1 will be F1 plus F1, that will be F1 plus F1, it means 2. Now, if you see, okay, it means the mean value theorem is satisfying here. If you see Z0 into Z1, G0 into Z1 is less than 0. Now, D option can be a choice. We will see later when we will compare with A. Now we see C option. The maximum value, it is not correct. In the 0 to 2, the function can any value. The function can any value. It is not given. It is -1 at 0. If we take the graph for B, suppose you have at 0 it is -1 and 2 it is -1. So between these values, function can any maximum or minimum value. Maximum or minimum value, we don't know the exact value. So we cannot claim the maximum or minimum of this function here. So this is not correct, this is not correct. Now we will check for A option here. Then we will compare with D option. This is a very interesting question. If we take A option and suppose GPH FP minus FP plus 1 and P belongs to closed interval 0, 1, then G0 will be F0 minus F1. It will be -1, -1, this is -2, and G1 will be F1 minus F2. It will be 1 minus plus 1, it will be 2. It means G0, G1 is less than 0. So we can apply intermediate mean value theorem here also. If you see, then what is the meaning of this? Then there exists at least one y, we are taking particularly y, between open interval 0, v, where gy is equal to 0. This is your intermediate mean value theorem. If this function is satisfying this property in 0, 1, then between 0, 1, g function will have one root where function is 0. We are taking particularly y notation here for our question purpose. It means gy equal to 0. It means fy, if you take gy from here, fy minus f of y plus 1 equal to 0. So fy equal to fy plus 1. So A option is correct. Now, why not D? So let's start more theory on this question. If you take D option, then you have GPH FP minus plus f of 2 minus p, and G0, G1 is less than 0. Then again, you have a y between open interval 0, 1, where gy is 0, means fy plus f of 2 minus y equal to 0. It means fy equal to minus of f of 2 minus y. So both A or D are correct, and why D is not correct? Why D is not correct? Let's start first. Y is between 0 to 1 I am taking. Then see the domain of this function. Minus y will belongs to -1, 0. -1, 0. And if we take, then your domain 2 minus y belonging to, if you add 2, you will get 1, 2, which is also a subset of 0, 2. It means we can apply intermediate mean value theorem, because it means this function is 2 minus y is also continuous in the given domain. And similarly for A option, if you see, if y between 0 to 1, then y plus 1 belongs to 1 to 2. This is also subset of 0, 2. It means function is continuous in this case also. So according to mean value theorem, both options A and D are correct. A and D are correct. Both option A and D are correct according to intermediate mean value theorem. Here both options will be correct. And I'm giving you homework if you see more on this question. Okay, thank you.